All right, so in these problems here, we're still working with Maclaurin series, but we're not constructing them and computing them from scratch. We are using existing series that we know about. Whenever you recognize, like in part A, e to the something that's not just x, you can just substitute. So let me show you 1a. We know it's given to us, and this should be on your formula sheet as well, that e to the x is 1 plus x. I'm just copying this out of the textbook, plus x squared over 2 factorial plus dot dot dot. Basically, what you've got is x to the nth over n factorial, and you're going on forever and ever and ever. So there should be another ellipse on the right side there. And so what you can do then for e to the 3x, this is just a nice trick, is just substitute 1 plus 3x plus 9x squared. You may wonder, wait, I thought it was substituting 3x. Well, I squared it. I squared the 3. So 9x squared over 2 factorial. The next one, I guess, would be 27x to the third over 3 factorial plus etc. And so it's a really nice, I say it's just substitution. It's a really nice, efficient way to get a more complicated Maclaurin series. When you look at something like part C here, you want to use the binomial series, which again you can get from the very same concept, but often we call these binomial series. So if we have 1 plus x raised to a power, this is something we did back in Unit 1, we can say that's 1 plus px plus, then it's like a factorial, p times p minus 1 over 2 factorial x squared plus dot dot dot, and it goes on forever. And so if we had like part C, the way I would write that is as 1 plus 2x raised to the negative 1, because it was the denominator of a fraction. And so we have 1 plus the p-value is negative 1, so negative 1. The x was substituted for 2x, so 2x like that. And then plus, the next one goes negative 1 times negative 2 over 2 factorial times 2x squared, etc., etc., etc. So negative 1 times negative 2 times negative 3 over 3 factorial and 2x to the third power. And so this is just a very efficient way to handle more complicated Maclaurin series. And you'll be able to see that this really does work. Let's go back over to our examples here. So we're going to go 1 over 1 plus 2x. There's our function. And we're going to go 1 plus negative 1x plus negative 1 times negative 2 over 2x squared. Okay, we're starting to approximate it. Plus negative 1 times negative 2 times negative 3 over 3 factorial x to the third. So we're getting closer and closer. We could keep this going on forever. And actually, there is a really nice way we could simplify here. I'll do that in the next one, because I want you to notice that what we have is really we have the factorial terms in the numerator and in the denominator. And so those are going to cancel out every time. And all we really have to do is count, are we even or odd, for if we're positive or negative. So the next term would just be negative because it's an odd power, and we'd raise to the fifth. The next term would be positive, and we'd raise it to the sixth. And so we can do all of that. And I forgot the one thing is that this was substituting just the x value. So excuse me, if I do this, now the approximation is good. And now the point that I was trying to make is that you can change the x in the original green function to 2x, and as long as you also replace each of the x's in your approximation with a 2x, you're still going to get a good approximation. So as I go through and add in these 2x's, you can see how the purple function will again approximate the green function. Almost there. And so this is a really nice shortcut because no matter how complicated I make the original function here. I mean, I could make this number whatever I want and then just substitute it in for all of the x values, and I'll get a dang good approximation. So there you go. I'm going to make one more video on Maclaurin series because there's a nice connection where they allow us to compute limits that we wouldn't be able to compute otherwise.